So yeah, my name is Gregory Dzhezyan. I go by Greg. I'm a master's student at California State University, Fresno, and we're going to be discussing a project that I worked on for my advisors who couldn't make it today. Dr. Hovhannes Kulanjian is a professor at Fresno State. He's my main advisor. And then Dr. Michel Kulanjian is another advisor, and he's at Rice University. So we'll go over some of the motivation for this project, a little bit of background, talk about what the project goals were. I'll go over some theory, try to go through that quickly, and then we'll look at the implementation and then some results. So we'll start with an introduction. So kind of one of the biggest, obvious, never-ending problems in communications, right, is the problem of data rate. Users want access to their information anywhere, anytime, and they want it now. And that's sort of that problem is sort of compounded today by the fact that we're streaming a lot of content, like our audio and video, and data formats for that content are increasingly becoming more and more high quality. And additionally, people are moving their storage from local storage to the cloud. And so, we're faced with this problem of data rate. And so spectral efficiency of the communications infrastructure that we have today is sort of important to meeting future demand for data rate. And we've seen communication engineers evolve, meet this, problem head on. Right, and we've seen with the evolution of cellular network infrastructure from 3G to 5G, and so what faster than Nyquist signaling promises is that spectral efficiency. So we know classical Nyquist signaling, right? The ISI criterion tells us that for some given channel bandwidth, W hertz, that the maximum ISI free signaling rate is 2W. But faster than Nyquist signaling works in a regime that is, that is faster than that. But the problem is it introduces ISI, and ISI, although we can deal with it, it introduces way too much complexity in the receiver. And in the 1970s, the famous sort of work was by Mazau, where he did an analysis using a minimum Euclidean distance detector, and he was able to show that a potential 25% increase in the signaling rate for the same given BER. Okay, let's talk about the project. So my advisors are interested in faster than Nyquist signaling. They've published several works on it in the past, but what they were looking at with this project was trying to see if they could implement a test bed in the lab for FTN. And that's because a lot of work on FTN is simulated. And so this would be kind of a pretty big departure from a lot of the work that exists. And we wanted to use things like software-defined radios and GNU Radio for the signal processing. We also used some MATLAB. But additionally, on top of that, they had recently published a paper where they had adapted an algorithm from another domain called the probabilistic data association algorithm, and they wanted to see if we could use that on the test bed. So we'll dive into some of the theory here with intersymbol interference. So there's sort of two domains in which we can think about communications occurring in. There's the wireless and the wired. So sort of the physical origin of ISI in the wireless domain is multipath. So when our signaling period right, is very large, multipath isn't the ISI caused by multipath isn't that big of a deal. But when that signaling period begins to shrink and becomes on the order of magnitude of the delay for the multipath, then it's a big problem, because that phase shift that occurs at the receiver for that second signal that traversed a different path is much larger, right? And then sort of the same thing in the wired domain. When that pulse duration shrinks, we have to start looking at the wire as a transmission line and modeling it using the parasitic effects of the transmission line. And it behaves as a sort of filter, and you get this smearing of the pulse. So we'll look at where ISI sort of comes from analytically, and we'll define some terms here. So I've got a very oversimplified kind of architecture for transceiver here, where we have our information bits coming in. They get converted to symbols, upsampled. They go through a pulse shaping filter, and that forms our transmission signal S of T. S of T traverses some channel. You get additive white Gaussian noise, and that forms R of T. And then we have our matched filter. The R of T gets match filtered, which forms Y of T. We get our downsampling that happens there. And then we theoretically have our symbols back at that point, and we get our information bits back. So defining some of those terms mathematically, the transmit signal, S of T, we can think of as sort of a train in time of whatever our pulse shape is. So our symbols in this case were BPSK, so it's just a very simple pulses, positive and negative pulses, right? And then that signal traverses the channel, gets convolved with the channel impulse response. So R of T is in terms of H of T, which is the convolution of the impulse response of the channel and the pulse shaping filter. And then finally, we match filter, and Y of T is written in terms of X of T, where X of T is that triple convolution there between our matched filter, our pulse shaping filter, and the impulse response of our channel, and we have our noise term. So after sampling, right, we substitute T equals MT into Y of T. And theoretically, we have our symbols back at that point. So if we write out a few of our terms here, what we'd like is at the first timing instant to recover our first symbol, and we can see there that A of 0, our first symbol, is being multiplied by this term X of 0. And then at the second timing instant, what we'd like is to recover our second symbol, right? So we can see a sort of similar structure there. And so if we separate out our symbols of interest and rewrite Y of T, we can see where ISI, those extra terms there, collect them up into that sum, and we can see ISI analytically here. So what we'd really like is for that middle term to not exist, and just have our symbols of interest plus the noise term. And the Nyquist ISI free signaling criterion tells us that, so if we want that behavior from X of T, where when T equals 0, we just get our symbols of interest and our noise, then the necessary and sufficient condition is that the spectrum of X of T, the frequency shifted sum of the spectrum of X of T must equal a constant. And so the proof of that is available in many communications textbooks. But if we think back to what X of T was, it was defined as that convolution. And we really can't necessarily do anything about the channel there, but the pulse shaping filters are within our control. And so, theoretically, we could meet, that behavior that we'd like from X of T. But we have to consider that with respect to the band limitation that we have. And when we do that, sort of three cases pop up. So there's the case one, which is the regime in which FTN signals. And so what we're looking at there is the spectrum of X of T, the frequency shifted copies of the spectrum of x of t. And we can see that, when we signal at that rate, we've got nulls there, and so we can't get that constant value. And so really, if there's no x of t that will not produce ISI there. And then in the second case, we signal at our sort of the maximum allowable frequency within our bandwidth. And really the only thing that can happen there is if x of t, is a rect function, which we know is a sinc in the time domain, but it's very unappealing to work with, very difficult to work with a sinc. And then sort of case 3, which most modern infrastructure sort of works in, which is signaling at a rate lower than the maximum allowable frequency for our band limitation. And so we can see there that potentially there are filters that we could design, and of course the most popular is the raised cosine. So for FTN signaling, the model is a very small change. So I previously defined that the transmit signal, was this sort of pulse train, and what FTN does is just adds another parameter, tau, to that equation, and we can and tau in the range is from 0 to 1, and we can think of tau as sort of a compression factor that forces those pulse shapes, the pulses, to come faster. So to implement that, we can sort of discretize that and take a look at what's going on there, right? We can represent SFTN as a convolution between our pulse shaping filter and our actual train of symbols. And we can see that tau sort of just affects the upsampling factor. So this is just, sort of giving a look at the extremes for tau. So when tau equals 1, we don't have FTN signaling. We can take a look at that at the top left, the top right for you guys, where you can see we've placed the RRC shaped symbols, and the sum of which would be the overall transmitted waveform, which is located in the next column. But when we lower tau to 0.2, something you wouldn't want to do, it's very extreme, we can see how those RRC pulses, symbols, have now sort of moved back in time. The ones that would come later have sort of moved back in time by about 80%. And we can see what that does to the overall transmitted waveform, where it's very difficult to recover all of the bits that were transmitted in that case. So this is a sort of another look at the effects of FTN. In the top graph, we've got tau equals 1. So we can see how long, sort of in duration, that waveform is. We might even be able to visually sample that waveform and recover the bits. And then when we lower tau to 0.8, we can see how the effect, how that waveform has now shrunk in time. And still here, even though it's become, the waveform has become a little distorted, we may still be able to recover the bits there just by even going in and visually sampling it. We may make a few errors, but that might be okay. And then when we lower tau to 0.6, at that point, it's sort of, the waveform has become very distorted, and we may make a lot of errors in trying to recover the information bits that were sent. Okay, so we'll move on to the actual implementation. So for the implementation, I just sort of followed that sort of generic architecture that was shown at the beginning. So this is the flow graph for the transmitter. So we've got our sort of bits to symbols that are happening there, our pulse shaping filter, which is the root raised cosine, and then what happens is some null values are inserted in between packets just for detection later. with that last block. So for the receiver, we do a little bit of low-pass filtering in the beginning after reception, and then it passes through a matched filter, and then that data gets written to a file, which then gets imported into MATLAB to work with. So the experiment we ran was we transmitted 10 packets for each value of tau. What we wanted to get was a BER curve of tau versus sort of bit error rate. So 10 packets transmitted for each value of tau. The packets had a 64-bit preamble, 10,000 random bits in the payload, BPSK modulated bits, and RRC shaped symbols. Our USRPs were just in a wireless loopback configuration, and we varied tau from 0.5 to 1. So MATLAB was used for some of the analysis, and all we do there is do some correlation to detect the preamble and detect the individual packets, and then downsample and then feed that to the PDA algorithm and also the minimum Euclidean distance detector. This is another figure here, sort of similar to one I had in the in an earlier slide, but now we've got actual data captured from a USRP with the transmitted FTN signals, right? So in the top waveform, we still have tau equals 1, and we can sort of see the extension, how long that waveform is. And then tau equals 0.8 in the middle, and tau equals 0.6 at the bottom. Next to them, you can see the eye diagrams for each of those, and we can see how that how the eye is beginning to close as tau begins to come down. So we'll go over some of the results here. One of the first things we did was just simply connect the transmitter to the receiver through the channel block, and we just used an ideal channel, so there was no noise, no multipath, nothing, right? And sort of the results we got were that, you know, the PDA algorithm and the minimum Euclidean distance detector, they both end up making, in the simulation, making no errors up until tau hits 0.8. And then we can see that sort of PDA looks like it might make less errors, but at that point, around 0.7, but at that point, there's just way too many errors for either of them to be useful. So then we went to using an actual USRP, the 2920. Again, it was in a wireless loopback configuration. And sort of here we can see that the PDA algorithm sort of behaved similarly to the simulation, where it didn't begin making errors until tau equals 0.8. But then it starts making a lot of errors. And then we additionally tried with another USRP, the X310. Here we can see that you know, their performance was sort of similar using this USRP, and they started making errors almost immediately. This data was sort of captured last minute, so what was done in this project, we were able to create a test bed for FTN signaling, and then capture data at various values of tau and feed them to these two different demodulation algorithms. So for future work, you know, we're still planning on experimenting with our test bed and capturing more data. But additional future work could involve extending the testbed to higher constellations, or potentially looking at implementing FTN for frequency, where, you know, you would have non-orthogonal NOFDM, and then a potential mix of the two, where you have time and frequency domain FTN. And so that's it.
So we have a fair bit of time. Are there any questions in the room? Yeah.
So from your results and the paper you cited, it looks like 25% is the limit of what you can do. Are there thoughts or ideas to try and push that higher, or do you think that's the theoretical limit of how well you can do?
So yeah, so that is the theoretical limit, and so that is about tau equals 0.8, and so that's what we're seeing from our experiments. So I'm not sure if that could be pushed higher.
So I have a question. When we're talking about theoretical limits and their relation to practice, is there any explanation for why your measurement results suggest that MED works differently than PDA in practice with a USRP?
Sorry.
Why does this work differently in theory and practice with a USRP, and why is it so different for two different USRPs, which I'd assume should have been pretty similar?
Well, we did sort of see somewhat. So from the simulation, right, that would sort of represent the theory, right? And we saw that PDA and MED didn't make any errors up until 0.8. Why? So why? I mean, that's sort of the great question always, right? Is like, why doesn't theory translate to practice? So yeah, that would require us to sort of look further and see what's going on there.
Cool. Thanks.